Hello, my name is Xu Wang, one of the author of this domain-specific neural machine translation for software localization paper, and now we're gonna present our work to you guys today. So, the definition of software localization is the translation of a software interface and messages to another language plus adaptation of some formats. So, in our scenario, this basically means the translation of mobile application or software text. And the market is huge because obviously the number of softwares and mobile applications is exploding these days, and the need for translating them into another language, the need is very huge. But when we actually want to do the localization process, we may encounter some severe problem. The current approach to do this is to hire human translators to do the translation tasks, and if you want to apply some machine translation techniques, such as using existing translation tools like Google Translate, it will not always produce a satisfactory result. And the Google translation system cannot handle those domain-specific application text, which is very common in the mobile application area. So taking this word Steam as an example, in the gaming software, in the gaming application, Steam may refer to the video game platform developed by Valve. But if you put Steam into Google Translate, it will just give you the original meaning of this word, which is vapor. So our goal here is to develop a neural machine translation system which can deliver acceptable translation for application text while still being able to handle the domain-specific words, just like the Steam word example. So to do this, we first have collected a huge data set. We've crawled around 80,000 applications from Google Play Store, which are basically all Android apps, and we extracted around 7 million training pairs from those APK files, including Arabic, Chinese, French, Spanish, and Russian, which are all UN official languages, which we think is representative for the current language systems. Our model is built upon a sequence-to-sequence model, which consists of two parts. One is an RNN called encoder, another is another RNN called decoder. The encoder may take the input sequence. In our case, it is the source sentence in the source language, and it will transfer it into a context vector C. And our decoder will use this context vector plus the previous word from the input sentence to generate the output, which is, in our case, the sentence in the target language. To make our model achieve better performance, we've made several modifications. The first one is we have incorporated category information in our model. So apps belongs to different categories, maybe tools, maybe news, games, or communications, and the same word may have different meanings in applications of different categories. So taking this driver word as an example, it can mean people that drives cars. It can also mean a program that controls software in computer science field. So these are a list of categories in Android applications, and to incorporate this information in our model, we first giving every category a special token, basically their name, and we append this token to the beginning of each sentence. So a sentence, this is the original sentence, and after do the appending process, we will have a special token indicating the category of the sentence's original application. So taking our driver word as example, if this select your Wi-Fi driver sentence belongs to an application which falls into a tools category, we will just append the category token of tools category at the beginning of the sentences, and the same thing happened for this please contact your driver sentence, which belongs to a transportation application. The second modification we've made is how we deal with the rare words. Rare words means that refers to words that appears only a few times in the whole corpus. could be people's name, address, URL, and placeholders. A traditional approach to treat the rare words is just mark them as one single UNK for all rare words. But in our model, instead of simply mark them as a single UNK, we also preserve their relative position information. So look at this example. In the original sentence, there are two placeholders and a URL. So we pre-process it, not only marking them as an UNK, we also preserve its positional information. And in the translated sentence, we will have the positional UNK preserved, and then we can easily map them back to the original placeholder. The third modification we've made is to deal with those short and common sentences. So some sentences and words are very common and share almost the exactly same meaning among all applications. And these words don't have much changes in meaning, so we've developed a dictionary-based mechanics for those sentences. So when we encounter the translation of such a short and common sentence, we just look into our dictionary and instead of put them into our neural model. This will increase the efficiency and accuracy of our translation model. We've done experiments to show that our model actually achieved the better performance. The evaluation metrics, including the blue score, which is the most applied metrics for evaluating translations, and we also use exact match rate, which refers to the exact match rate of our translated sentences, comparing with authored sentences. We also chose Google Translate as our baseline method. We've conducted experiments on around 20 Android applications, and our model has outperformed Google Translate in terms of both blue score and exact match rate. We've also done similar experiments on all of the 5 UN official language tests languages, and it shows that our model also outperforms Google Translate in all of those 5 languages, which means our model has the ability to generalize to other languages. That's basically what we want to present today. Thank you so much for listening.